This video is about interval estimation. So if we're constructing a confidence interval for mu, that would be an example of interval estimation for a population parameter. Mu is the parameter. We're doing an interval to estimate mu. So I want to talk a little bit about what that really means. We take a sample from a population and the sample mean is x bar equals 44.45. And with the data we have, the margin of error is 2.4, and we want to make a confidence interval with a 95% level of confidence. Let's look at what that looks like and what it means and what happens if we keep repeating the process. So here we are taking 19 more samples and calculating x bars for each of those samples. Got the same margin of error to create 95% level of confidence intervals. If you look here, for this example, the actual population mean is going to be 44. And each of those confidence intervals is represented by a bar, saying the mean is 95% confident the mean is between here and here. Well, hey, it is. My point estimate was a little bit high, but my interval contained it. The next one, my point estimate was a little bit low, but the interval contained it. And on down. This one almost spot on pegged it with the point estimate. Here, this one missed it. Well, that's what it means, really, to be 95% confident. It also means that over time, because of the law of large numbers concepts that we learned, 95% of them will contain the mean, like all these did up here nicely. But 5% of them won't. 1 out of 20 will miss it even in the interval. So the more you want to make sure you hit that mean, the higher confidence level you need to have. Therefore, the wider confidence intervals you need to have. So when you estimate the mean of a population, you're going to take a sample and find x bar. And use x bar as an estimate for mu. But we're going to assume that there's some error. It's not going to be all that common that you'll find a sample will have the spot-on same mean as the population does. And we figure out the margin of error based on what's called, we'll call it the margin of error, and we base it on the z-score, which we'll talk about in a minute, standard deviation, and the square root of n. This should look familiar to you from central limit theorem, because this is the standard deviation of our sampling distribution. Z star figures in the confidence level, because it'll be the point on the curve, the standard normal curve, that captures the right percent of the sampling distribution. So there are typical levels of confidence that we use for confidence intervals. And the z-stars we refer to as critical values. You need to write these down and you need to know them, because it's usually going to be easier to figure a margin of error just by using the formula than by having to backtrack off of your calculator. I will show you in another video how to do confidence intervals on your calculator, but it's typically easier to do if you're just asked for margin of error to use these. You just need to know them. So here's what they are. And these are the places on the normal table. So 90% is going to put 5% in each tail, and this will correspond to 0.05 on the normal table and on down. So once we know that estimate for mu, the x bar, and the margin of error, then we find out the confidence interval by adding and subtracting the margin of error. So I'm either that far below my x-bar or above my x-bar. That's going to be the range that I will consider as my confidence interval. So here is an example. I want you to pause the video and read this carefully. This table is your data. So you're going to need to find the mean of that and try to create a 95% confidence interval with this, assuming a population standard deviation of 8. So pause the video, do the work you need to do to figure that out, then start the video again. The next slide has a solution. Okay, so the x-bar, when you put that all in, is 25.667. I have kept 4 decimal places throughout my calculations. I suggest that you do at least that. For most things, it's just best to keep, if there's only 5 or 6 decimal places, just keep it throughout all your calculations and don't do your rounding until the end. Because if you round too early, you might end up getting rounding errors and your answers won't be taken as correct. So the x-bar I got was 25.667, sigma was 8, and n was 18. For every problem, write those 3 pieces of information down, because they're what you're going to plug into your formula. And then you're just going to take your z-star, this was a 90% confidence interval, is 1.9, it's a 95% confidence interval, so your z-star is 1.96. 8 was your standard deviation, 18 was your n. When you do all these calculations out, that's your margin of error. Subtract it from x-bar and you get this number. Add it to x-bar and you get this number. So check your work on that, and if you have any questions, let me know. Now we're going to move on to population proportion confidence interval. Same exact concept, except this part is different, and that's the only thing that's different really on this. We estimate p with p hat, just like we estimate mu with x bar. And we get a standard error for the sample proportion that we use along with the z-star. So the standard error, we basically use it's basically the same thing. It's pretty darn close. It's we substitute p hat for p to help us get the standard deviation, then we divide by n, and we take the square root of the whole thing instead of just the square root of n. So that's the formula that you need to know. Make sure you have that written down. And then this is it. You take your p hat that you've done, add or subtract z-stars, same z-stars, same critical values, times this whole messy formula, p hat times 1 minus p hat over n, square root of the whole thing. Now, only use this when successes and failures, and by successes and failures, we just find it the yeses and nos, or the, each end of things, each thing that could happen, you have at least 15 of each. Otherwise, you're not going to get the right information out of this. So that is your big, that's your big criteria, along with the fact that you've done a simple random sample. So here's an example. So again, I want you to read this carefully, do the work of constructing this interval, and then go to the next slide. So pause the video while you do that, and then go to the next slide to check your answer. So here we have it, our standard error. Well, p hat was 0.62. When you divided the number that had kids, 124, by 200, you should have gotten 0.62, which makes 1 minus p hat 0.38. Divide that by 200 and take its square root, and you get 0.0343. So now you take that p hat and you add and subtract the critical value, 2.576, times that standard error. And when you multiply these two together and add it and subtract it from 0.62, you get 0.5316 and 0.7084. I think it said on the problem to round to 3 decimal places, so that would be 0.532 and 0.708. Both these example problems, I will do a calculator video that will show you how to do them both on your calculator.